Alright, so I'm going to be telling you about the study I've been working on, looking at the effects of the recent extreme drought on annual seed banks in California grasslands. Alright, so in these grassland communities, we have these two major players, right? So we have our exotic annual grasses and our native annual forbs. And it's really the exotic annual grasses that dominate the landscape in terms of cover, but they're really low in species diversity. In our field site, we have about 13 species, but it's really these four that are the most abundant. Native annual forbs, on the other hand, contribute by far to the species diversity of this system. We have about 130 species in our study site alone, and they're a really important part of the community, not only as a component of the larger California floristic province, but also as a crucial resource for a lot of our native pollinators. And these two groups are really in direct competition with each other. So grasses form these dense layers of thatch that can inhibit forbs from germinating, and they also have really high relative growth rates. But they also have short-term seed longevity. Native forbs, on the other hand, have much longer-term seed longevity, and that leads to the creation of seed banks that really help buffer their populations from declining during unfavorable years. So beginning in 2012, the California floristic province began experiencing one of the most extreme droughts in the past 1,200 years. So this is a graph of the Palmer Drought Severity Index, which measures the severity of drought, since the year 800. And you can see by the dashed red line at the bottom that the 3-year period from 2012 to 2014 was so extreme, it was at a negative 14.55. Which is predicted to only have a return interval of about 10,000 years. So it was really extreme and really rare. And this entire drought is nested into this larger aridification trend. So my field site's at Lake County, California, at the McLaughlin UC Reserve. And this is a graph of winter precipitation over the past 16 years. And winter is really the most important part of the growing season for a lot of these annuals. So you can see highlighted here, those are the drought years, but even beyond the drought years, you can see this pretty significant declining trend. And with climatic warming, California is really just projected to get drier on average, but with a higher frequency of extreme events like this. So in response to aridification and drought, we see these widespread ecological consequences, including things like loss of species diversity, lower primary productivity. Recently, there's been a lot of papers linking the drought to large-scale tree mortality. But drought really also acts as a filter, and we often lose the least drought-tolerant species first, such as shallow-rooted species, or what I'm going to be focusing on, species with high specific leaf area. So specific leaf area, measured as leaf mass over area, is negatively correlated with water use efficiency. So species with lower specific leaf area are typically more water use efficient, they're more drought tolerant. Species like this from my field site are Plantago erecta and Calicadenia passiflora. On the other end of the spectrum, we have species that have larger, thinner leaves, and these are typically less drought tolerant and have lower water use efficiency. And two examples of that would be Nemophila heterophila and Euphorbia crenulata. So we've already seen some effects of this drying trend at my field site. This is a graph of the number of species over 5 square meters over the last 16 years. So you can see that the exotic grasses haven't really been doing much in terms of diversity, but it's really the native forbs that have been declining, both on this harsher serpentine soil and on the richer non-serpentine soils. And in addition to this declining diversity trend, we're also seeing this declining trend in weighted specific leaf area. So we're weighting the average specific leaf area of a plot by the relative abundance of each species in that plot. So not only are we losing species diversity, but we're also losing the least drought tolerant species first. But what about the seed bank, right? A lot of these forbs maintain seed banks. They're supposed to buffer their populations against these drying trends. So we wanted to know whether or not that was the case. We had multiple questions for this study. I'm going to be focusing on these two. First, whether or not seed banks of these native forbs or invasive annual grasses show any signs of depletion in response to the drought. We would expect forbs, which typically have more persistent seed banks, to be better at buffering their populations from declining than the grasses. And second, we wanted to know whether or not the composition of the seed bank shifted towards a more drought-tolerant community, using specific leaf area as a proxy for that drought tolerance. All right, so to answer these questions, we compared seed bank composition before and after 2 years of extreme drought in a set of sites at the UC McLaughlin Reserve. At the reserve, we have these 80 sites across 27 square kilometers of the landscape. We have 42 sites in these non-serpentine richer soils here in red, and then 38 in serpentine here in green. And this is the same data set that we found the declining diversity trend in and the declining specific leaf area trend in. So we can really place what's going on in the seed bank into the longer term context of these trends. All right, so at each of these 80 sites, we have a 50-meter transect with 1 square meter plots spaced out along that transect. And my advisor, Harrison, and her lab have really been visually estimating cover for the past 10 years at these sites. And they measured specific leaf area back in 2010. Then in 2012 and 2014, we collected soil cores from the top 10 centimeters of the soil, so just getting that really where the main part of the seed bank is. And we collected 1 from each of the 5 subplots and then aggregated it to give us 1 sample per transect site. We spread each of those samples out in a flat and placed them in a shade house, so they're open to natural background temperature variation, but we induced germination by watering them daily across the growing season. And then we identified and recorded every season that came up. We allowed the flats to dry down for a summer, and then we resumed this whole protocol for another growing season in an attempt to exhaust what we could of the seed bank. And in each year, we counted over 11,000 seedlings from 159 different species. So we're really learning a lot of information just from those small soil cores. All right, looking at our first results on abundance. So this is a graph of the number of seeds we found per site over the course of this study. And focusing just on exotic annual grasses, you can see they started off really strong in 2012, especially on the non-serpentine soils, which makes sense. Non-serpentine areas of grasslands are usually really heavily invaded. But by 2014, their populations really crashed. They fell by 60% in non-serpentine areas and 31% in serpentine areas. When we overlay the forb community on this, we see the exact opposite trend though. They increased a lot on both soil types, by 123% on non-serpentine and 250% on serpentine soils. And this huge increase really highlights just how important the seed bank really is for this community, but also shows the disproportionate negative effect the drought is having on the grass community compared to the forbs. But then we wanted to know, why did it increase so much? When we think about seed banks, we think about them as stabilizing the above ground populations and not necessarily tripling in number. But this is really clarified when we look at the community-weighted SLA data. So focusing first on the above ground, this is what we saw above ground in our 2 years of the study. Not much of a change on non-serpentine and a small but still significant decline on serpentine. When we compare this to the community-weighted SLA in the seed bank, though, now in blue, we start to see that our focus above ground really skews our view towards these lower SLA species, right? So the seed bank has significantly higher weighted SLA across years and soil types compared to what we see above ground. So the seed bank really is acting as a reservoir for these the less drought tolerant, higher SLA species. But weighted specific leaf area is also decreasing over the course of the drought, so we are seeing these communities shift towards a more drought-tolerant assemblage. But it's not because we're losing those high SLA forbs, it's because we're gaining low SLA ones. And that's really pulling down the community-weighted SLA. Focusing on the serpentine community on the right, you can see that there isn't as big of a decline, and the above ground and below ground portions of the community are much more similar. And this really makes sense because serpentine soils are already pretty harsh, so the species that thrive there are already adapted to a more stressful, rockier environment, which is also probably why we saw such a large increase on these soils. Seed bank on non-serpentine soils, however, showed a strong decline in specific leaf area, which is interesting because we don't really see this reflected above ground. So there's a bit of a discrepancy between what's going on above and below ground here. So if we zoom out and kind of place these changes into context, we can dissect what's going on here. So this is the same graph I showed in the beginning, just looking at the declining SLA data trend over the past 10 years in orange, and then with the seed bank data overlaid now from the tiers of the study. And this way we can kind of start to see how the above ground and below ground portions of the community really feed into each other. So if we focus on 2011, the year before the drought and before our seed bank study, we see that the above ground community had a relatively higher SLA compared to the other years. So we can imagine maybe it looked like this simplified figure here, with a higher number of the purple high SLA forbs and a relatively lower number of these orange low SLA forbs. So 2011 was probably a really good year. The high SLA forbs produced a lot of seed, it went into the seed bank, but we don't see that reflected above ground because 2012 was already a pretty dry year. So in this way, the seed bank in 2012 is kind of showing us what the community used to look like. So it's giving us a window into the past. Focusing on 2014 now, we see this buildup of these lower SLA forbs in the seed bank that haven't really contributed to the above ground SLA yet. By 2015, however, that shifts and it pulls down the community-rated SLA. So in this way, seed banks can also tell us what future communities may look like. So quickly to recap, we saw a strong decrease in exotic annual grass abundance over the course of the drought, but stronger increases in native forb abundance over the course of the drought. But we also saw a decrease in community-rated SLA, so the seed banks are shifting towards these more drought-tolerant communities. And seed banks are harboring those higher SLA species over the course of the drought. But what does it all mean? Well, the seed bank is clearly maintaining diversity in the system with the current year-to-year changes in climate. It's doing a good job of maintaining these native forb species throughout the drought. But it's possible that longer-term aridification will lead to lower SLA assemblages, favoring these more drought-tolerant species. Beyond that, seed banks can also tell us what a community used to look like in the past or what it may look like in the future. I think one thing that's really clear from this study is that the drought disproportionately negatively affected those exotic grasses, so it's a small silver lining of the drought. In general, I think this all just highlights how important this often overlooked part of a plant's life cycle really is. And that is all. And bonus points if you can identify any of these little